In the same time, we'll also briefly look into the little bit of theory that is relevant for understanding this particular experiment. To begin with, the aim of this particular experiment is to determine experimentally the emissivity of a test surface. As for the constructional details, what we have here is there are two plates which is made of aluminum, and these two plates are mounted on a frame. So this is the plate surface for which we are going to measure the emissivity. And these two plates are of the same material, and the dimensions of these two materials are also same. And the one plate is coated with dull black, and this particularly coated surface plate, which is also called as a black plate, or sometimes it is also referred in the video as reference plate, acts as a black body. And this entire frame on which these two plates are mounted is positioned in an enclosure, generally speaking, so as to minimize the heat loss from the convection, particularly by forced convection. Again, the contact between the frame and these plates is kept to minimum so that the heat transfer by conduction is also minimum. Particularly, we will neglect that component in the analysis. Here, each plate consists of two layers, and between those two layers, there is a heater positioned in each plate. The help of the heater, we can heat those plates, which in turn will be useful to calculate the emissivity of this test surface. Similar to the previous experiments, the power input given to the heater is controlled by this dimmer start, and here we have in this particular experiments there are two dimmer starts so that we can control the power input given to the test plate as well as to the reference plate. In this particular experiment, we will give two inputs which are different to the one input to the test plate and other amount of power to the reference plate. The amount of input is controlled by changing the dimmer stat, so which are showing this black box. And there are three thermocouples are used in this particular experiment. One thermocouple is mounted on the test plate, and the other thermocouple is mounted on the reference plate, which are useful to determine the surface temperature of the test plate as well as the surface temperature of the reference plate. Similarly, there is a third thermocouple which is used to measure the ambient air temperature as well as the surface enclosure temperature. We are assuming that the ambient air temperature is equal to the surface air temperature. Sorry, surface temperature of the enclosure. Here, as I have mentioned, the power input to the heaters in the test plate as well as the reference plate is controlled using these dimmer stats, and the power input is given to the heaters is measured in terms of voltage as well as the current using the voltmeter as well as the ammeter. So here we have voltmeter here, and this is the ammeter, and there are two knobs here which are useful to read. These are the two knobs. By moving them towards the top, we are reading the concerned voltage as well as the current that is flowing through the one heater. When we move these knobs to the downwards, we are reading the current and voltage associated with the particular heater, where the heater is positioned in, whether in the test plate or whether it is positioned in the reference plate. Here, these two knobs are only used to read the voltage and current corresponding to the particular heater. And this is the main switch. And similar to the previous experiment, so this is the temperature indicator selector switch. By using this temperature indicator selector switch, we can read the temperatures measured by the thermocouples which are mounted on the test plate as well as the reference plate as well as on the enclosure surface. From this black colored temperature indicator selector switch, and in this panel we can read the temperatures measured by the thermocouples which are mounted on the reference plate as well as the test plate. And this is concerning the experimental setup. Now let us see first. So as Sir is showing here, by changing the thermostat position, we can appropriately change the power input to the test plate as well as to the heater in the test plate as well as in the heater in the reference plate. So here you can see SAR is changing these knobs towards the top and bottom so that we can appropriately read the voltage and current corresponding to the heater that is located in the either in the test plate or in the reference plate. For example, as you can see here, if we put these knobs towards the up, that corresponds to the power input to the heater in the test plate. And whereas if we move these knobs towards the downwards, then the readings in the voltmeter as well as in the ammeter corresponds to the heater in the reference plate, or as we can also call it as a black plate. As for the experimental procedure, first we'll keep these dimmer starts at zero position, and then we switch on the power supply. After that, we'll give some amount of power input to the black plate by slowly increasing the dimmer stat variac. And here the power input given to the black and to the heater in the black plate is slightly higher than the power input given to the heater in the test plate. Later we will discuss why we need to give a slightly higher power input to the heater in the blackened plate than the heater in the reference plate. So the power inputs are selected in such a way that at the steady state, the reference plate as well as the test surface, both of these surfaces are at the same temperature. The power inputs that are selected in such a way that at the steady state, that means when the heat input given is equal to the heat loss by all three other modes, same then the temperature of the test plate as well as the black plate does not change with time, then we can say that the system has reached the steady state. At the steady state, the temperature of the test surface is equal to the temperature of the reference surface. Again, to emphasize, the power input given to the black plate is slightly higher than the power input given to the test plate. And as for to obtain whether the system has reached the steady state or not, periodically we can note down the temperatures of the surface of the test surface as well as the reference surface using the temperature indicator selector switch. Once the system has reached the steady state, we can bring down the variac to the zero position and we can switch off the main supply. So this is the concerning the experimental procedure. And here note that if the power inputs are not known, we can fix the we can select some power input to the blackened plate, and after some time the surface temperature remains constant at the steady state. Then we can slowly, by using trial and error method, to change the power input to the test plate such that the surface temperatures of the test plate is equal to the surface temperature of the blackened plate. Although in this particular experiment, here we are giving you the power inputs that are required to achieve the steady state. I mean, here we are giving you already the what should be the power input to the blackened plate, that is the reference plate, and what is the power input to the test plate, in such a way that at the steady state both the surface temperatures are same. If one does not know those inputs, we have to use a trial and error method to find out those appropriate inputs to the test reference plate as well as the test plate heaters. Now let us see the little bit of theory behind this particular experiment. Again, let us see the manual. As per the experimental setup, this we have already looked into, and as per the specifications of the different parts of this particular experiment, the enclosure size in which the test plate as well as the reference plate are positioned is having these dimensions, and the plate having a diameter of 17 centimeters. Similarly, I already mentioned that test surface dimensions are same as the reference plate dimensions. So the diameter of the test plate is same as the diameter of the reference plate. And here we are using nichrome strip wound mica sheet type of heating element. And here we have two dimmer stats. We can so that we can control the power input to the heater in the reference plate as well as with the power input in the test plate individually. And these are the ranges of the voltmeter and ammeter, and again this is the range of the digital temperature indicator. The type of thermocouple is the chromal aluminum type. From the heat transfer cores, we have known that the black bodies are the ideal bodies which emit the maximum possible radiation at a particular wavelength at a particular surface at a particular temperature. And these are also ideal absorbers. That means they absorb all the radiation that is incident upon their surface at any wavelength at any temperature. Here in this particular experiment, we are assuming that the plate which is coated is acting as a black body. The radiation heat flux emitted from a surface is called as the emissive power. We can define the emissivity of a surface is equal to the emissivity of a surface at a given temperature is defined as the ratio of the emissive power of the surface at a given temperature to the emissive power of a black body at the same temperature. Note that the emissivity of a surface depends on the temperature. As per the emissivity definition for a simple surface, emissivity epsilon is equal to the emissive power of a surface at a given temperature divided by the emissive power of a black body at the same temperature. In this particular temperature, when we switch on the power supply and we change the power input to the heater, electrical energy is converted to the heat energy so that the plate temperature is increased, as soon as there is a temperature difference in the system, there exists a heat transfer. Heat transfers by all three possible modes. Here, in this particular experiment, we are assuming that as the contact between the frame on which the plates are mounted is minimal, so the heat transfer by conduction is assumed to be minimal. And as these plates are mounted in a closed enclosure, due to the change in density, there is a possibility of natural convection from the test plate to the air that is surrounding these plates for the both test plate as well as for the reference plate. At the steady state, power input for the black body is equal to the heat transfer by convection plus radiation from the black body surface to the surroundings. Similarly, for the test plate also, heat input given, that is Wt is equal to heat transfer by natural convection, you can say it as a natural convection or as a convection plus heat transfer by radiation. Here we are not assuming any heat transfer from the conduction. We are simply neglecting that the heat transfer by conduction is minimal. If we assume that one, as the test plate and the reference plate both have the same dimensions and they are made up of the same material and both surfaces are at the same temperature and they are also positioned in the same orientation, then we can assume that the heat transfer by convection from the test plate is equal to the by convection is equal to the heat transfer by convection from the reference plate to the surrounding fluid. Here the fluid is air. You know that the heat transfer rate from the Newton's law is equal to Q is equal to HA delta T. Delta T is Ts minus T infinity. Ts is the temperature of the test surface, I mean any solid surface. In the steady state, we are saying that the temperature of the test surface is equal to the temperature of the reference surface. So, and also the ambient air temperature is also same because they are positioned in the same enclosure. We can say that the delta T is equal to constant. Similarly, the both the test plate as well as the reference plate has the same dimensions. We can say A is equal to constant, and we can also say for this particular condition, the convective heat transfer coefficient is also same. Because of these reasons, we can say that WCVB is equal to WCVT. And if we subtract this equation from this equation, then we can write it as WB minus WT is equal to WRB minus WRT. WB is the power input to the reference plate, whereas the WT is the power input given to the test plate. We can read the voltage and current for the heater in the black plate as well as the voltage and corresponding current for the test plate as well as from the ammeter and voltmeter using the appropriate knobs. These two are the inputs that are given. Similarly, heat radiation heat transfer from a surface between two surfaces is for the black body reference surface and for the test surface can be calculated using these two formulas. Here, AB is the surface area, sigma is the Boltzmann constant, and EB is the emissivity of the black body surface, and T1 to the power of 4 minus T to the power of 4 minus this corresponds to the heat transfer rate from the black body surface, whereas WRT, that is the heat transfer rate by radiation from the test surface, is given by this particular formula. which is AT multiplied by sigma multiplied by epsilon t, that is the emissivity of the test surface, t to the power of 4 minus t to the power of 4. Here the emissivity for the black body is equal to 1, and we know the Stephen Boltzmann constant, and we already know the surface area of the test plate as well as the reference plate. Both of the diameters are same. We know the diameter of the plate as well as the thickness. We can simply find out the area. We can find out the area, and at the steady state, we are saying that the temperature, surface temperature of the test plate is equal to the surface temperature of the reference plate. That is T1 is equal to T2. And the T is the ambient air temperature, which is equal to the enclosure surface temperature. We can obtain this value from the third thermocouple. So we know all these quantities. Now we can simply obtain the emissivity of the test surface. And these WB and WT are the power input to the heater in the reference plate as well as the power input to the heater in the test plate. The procedure we have already looked into. Let us see the observation table. As I have mentioned here, the voltmeter and ammeter readings are given to you, and will set those appropriate readings for the heater in the test plate as well as for the heater in the black plate. After that, we'll periodically will note down the readings in the temperature indicator using the selector switch for every 10 minutes until the two consecutive sets of readings are same, so that we now know that the system has reached the steady state. We'll note down the surface temperature of the test plate as well as the surface temperature of the reference plate or the black plate, and also the enclosure surface temperature also. These are the three temperatures that we note down at two different power inputs to the heater in the test plate as well as the heater in the reference plate. As for the calculation procedure, as I have said, we'll obtain the enclosure surface temperature from using a thermocouple in the temperature indicator, which is which we get it in terms of the degree Celsius, will convert into the kelvins. And similarly, at the steady state, we know that the surface temperature of the test plate is equal to the surface temperature of the reference plate, which also we get from this, let us say the reference table. If we perform the experiment at the end of the steady state, you know T2 is equal to T1 is equal to Ts, and again we have some temperature value from the temperature indicator, which is again in terms of the degree Celsius. We'll convert it into kelvins. We know the heat input to the black plate as well as the heat input to the test plate. That is simply by multiplying the voltage with the current. The surface area, so we have the a circular plate with some thickness. Heat is radiated from the both sides of the plate. So we can write it as the 2 multiplied by pi d square by 4, and also from the circumference also, that is equal to pi d multiplied by t. So t is the thickness of the plate, that is equal to 6 mm, as per the diameter, which is equal to 170 mm. Once we have all these readings, we can simply substitute in this particular formula, which gives you the surface emissivity of a surface at a particular temperature. So this particular temperature is the temperature of the test plate, which is equal to the temperature of the reference plate at the steady state. In that particular fashion, one can find out the emissivity of a test surface at a particular temperature using the comparison method. That is concerning the theory, theory as well as the explanation concerning this experiment. Again, you can go through the video as sir has given has explained elaborately how one can change these inputs so that at the steady state you can reach the the surface temperatures of the reference plate can be made equal to the surface temperature of the reference plate. Surface temperature of the test surface to be equal to the surface temperature of the reference plate. So one has to do a trial and error method so that the inputs are selected in such a fashion that the at the steady state the surface temperatures of the reference plate is equal to the surface temperature of the test plate. So that's all concerning the theory as well as the explanation for this particular experiment. And we have two more experiments concerning the heat transfer. And after we finish those experiments, somewhere after your mid, mid exams, we'll have the minor. I will let you take in the due course. Vishnu, you can call out the absentees and see if anybody present.
Yeah. Who is Karthik Krishna? Karthik Krishna. Can you hear me, Karthik Krishna? It's okay, sir. I will call the absentees. Number 3. See, you have to attend the class from start to end. You should not come in between. Please remember. Number 3. Hello?
Sir,
Yeah. You should come to the class from start to end. You should not come at the end or in between also.
no, sir. I joined at 45 like that time.
Yeah, that is also not good. Okay, don't repeat it.
Okay, sir.
I can take attendance at any time. So you should be attend the class from start to end. Everybody, please remember it.
Okay, sir.
Yeah. Okay. Roll number 10. He also came.
Present, sir.
Okay. Roll number 11. 15. 20.
Present,
Sir,
sir.
19 is present.
Yeah, 19 is present. I asked only 20.
Yes, sir, present, sir.
Yeah, 20 is present. 24. 25.
Present, sir. 25 present.
Okay. 30. 31. 34. 36. 38. 42.
Sir, 38 present, sir.
38. Okay.
42 present, sir.
42.
Okay, what's your name? Okay, okay, Karthik Krishna is 38.
38, sir?
I think so.
Yes, sir.
So,
Can you put your name before your, sorry, roll number before your name so that.
Yes, sir. Sorry,
can
sir. I
attend-
changed it for another subject. So I just changed it back.
Yeah.
okay. You please change it. Okay.
Okay, sorry, sir.
Okay. Roll number 44. 45. 47.
Present, sir. 47 present.
Okay. 48, 52, 54, 55.
54, sir. 54.
Okay, 54 present. 55, 57,
Present, sir.
63,
Present, sir.
68, 76,
Present, sir.
81,
75, sir, also present.
75 also. Okay, okay. 81,
Present, sir.
86, 87,
Present, sir.
88.
Present, sir.
Yeah. You please follow that one. I can take attendance at any time. So you be present from start to end. And
That's it.
this experiment 3 submission I extended to till today midnight. Okay.
Yeah, sir. Thank you.
And you can upload experiment 4 after that. Okay. 2 weeks time you will have. Now, what about experiment 5, sir?
Yeah, we'll put the due date for this one also after the mid break,
That
somewhere
means
March 3rd. March 3rd.
okay. Okay, sir. Maybe
Okay.
after till March 3rd, we will take
Yeah,
the
yeah.
experiment 4. After that, maybe 2 days we will give for the experiment 5.
Yeah,
Like
until
that,
March 5th for this experiment file. Okay.
yeah, yeah. Okay, sir.
Okay, yeah, that's all, guys. So for this week, we'll again meet after the mid semester.
Thank you, sir.
Thank you.